UNH Observatory very frequently. So that's University of New Hampshire. It's over in Durham. So we have a similar night to this. We don't have the big discoveries.
Yeah, but still.
We're working on telescopes that can see through the clouds.
Yeah, there you go. Well, the planet Cherry will do that.
There you go. There you go.
This is very informative, and the New Hampshire Astronomical Society is outdoors, and it's clear that it's very good.
Oh yeah, absolutely. They do stuff in.
They're out there as we
They do that in Portsmouth
They
frequently too.
do? Where in Portsmouth?
Tom Cochiaro.
Tom Cochiaro is the guy in charge of that. Tom Cochiaro, he's in charge of the Astronomical Society over in Portsmouth.
Well, before the solar eclipse, they were going, they went to different libraries, and different men put on information about that, and I went to the one in Salem, New Hampshire, and I did go to Jericho, Vermont for the solar eclipse, me and my friend.
How far up is Jericho?
It's not that bad. I wasn't driving, but White River Junction area, not far from there.
Okay, so it wasn't total.
No, we had total. It was total.
Total?
Yeah, it was.
And it was a long ways up from White River Junction.
Well, maybe it was, but I wasn't driving and the traffic was tough, so.
Yeah.
It was.
Hello, everyone. Welcome this evening to Superstellar Friday. We are so excited to have you all join us for this wonderful evening's presentation. Before we get started, I just want to lay out a little bit of what the evening is going to look like. I know we have some new faces in the audience this evening. So this presentation is going to go from 7 to about 8 o'clock with lots of time for questions. So if you have those questions, definitely hold on to them. I'm sure our lovely speaker, Lance, is going to have wonderful answers to give you all about the Northern Lights and his research. After the presentation, we'll have a little bit of time to get some water, use the restrooms, and then head into our planetarium for a night sky presentation with our educator, Dave. There he is right at the front there for all of you. And then after that, we will have a little bit more time. The museum will be open until 9:30, so you can explore the exhibits. We also have the New Hampshire Astronomical Society outside. There are at least 2 telescopes ready to go, looking at some 3 telescopes ready to go, looking at some planets and other things in our sky right now. So it looks like it'll be a beautifully clear night for us to view and ask some questions about telescopes and other objects. Okay. But without further ado, I want to introduce our speaker for this evening, Lance Davis. He is a PhD candidate from UNH and the manager of the observatory out at UNH. And he's going to talk to us about his research with sounding rockets and the details that he built, all the things that he did to study the Northern Lights. So why Northern Lights exist, all of those things. They've been in the news a lot lately. I'm sure maybe some of you have seen them this month in the last couple weeks, which is wonderful. So without further ado, I will turn it over to Lance.
Thank you very much, Amanda. I'll do my best to live up to the expectation of wonderful and lovely. So I'll be talking about sounding rockets in the Aurora, obviously. This is a picture of the launch we had in Alaska last year in November. This little bright white streak here is the first stage motor. I'll get to a lot of the details on this later in the presentation, but there's some Aurora chasers, same thing as like tornado chasers or so on. There's people that chase the Aurora. And a lot of the pictures that I have in here are from similar Aurora chasers. So to start with, we've had a very lucky year for the Northern Lights.
Yeah.
Not only have we had 2 great displays, they also have been clear nights. So the 2 most notable ones that I'll point out is this large storm on May 10th near Mother's Day, and one earlier this month on October 10th or so. The 2 pictures here on the right are from May 10th. Larry Hamilton is kind of an enthusiastic amateur astronomer over in the Durham area. Same with Sabby Clemens, she works out at our observatory as a volunteer. They sent me these pictures and said, Aurora, Aurora, and then we had to run out and find it ourselves. John Gianforte, he runs the UNH Observatory. He sent out a couple of pictures on the Facebook page and I nabbed one to show off here. as a show of hands, how many of you guys have been able to see the northern lights this year? Dave, you haven't been lucky?
I know, it's
Okay.
awful. I tried.
Okay, good.
You don't have enough good friends to be.
I know, I don't know what happened.
So as I go, if anyone has any questions, please feel free to ask. This is more meant to be an interactive, fun thing to do, and I think it makes it a lot more fun. So with all of the aurora that's been happening over the last year, there's been a lot of headlines and articles of, there'll be aurora tonight, check your weather, go outside. And this frustrates me. Sometimes they're right, but very frequently they are, it's very skeptical. There might be a small chance if you're in the very northern tip of Maine, for example, and it's not very realistic. So one of the things that I want to go over today is how you might be able to accurately forecast it yourself, because it's something that you can do. It's not super difficult. It will give you better odds than just listening to the article numbers. So what I want to go over tonight is, what is the aurora and how does it form? How scientists forecast the aurora and study it. How our work here in New Hampshire, in the University of New Hampshire, uses sounding rockets to further that research. And then I promise by the end of it, I'll actually go over how to forecast it at home. So just to set the stage a little, what causes the aurora? There's three main things that go on here. There's three main actors. First one is the sun. Everything space weather-wise always goes back to the sun. Two is Earth. And three is the atmosphere of Earth interacting as the medium between the two. So start off, we have the big guy here is the sun. These are two pictures from earlier this year. We had a beautiful eclipse, also wonderful for astronomy this year. Again, very lucky year for us. Both of these pictures are from John Gianforte. He went up to southern Canada to view the eclipse. How many of you guys got to see the eclipse, either totally or partially? Wow, it's like you guys came to an astronomy talk.
Yeah, it's a great year.
So for me, one of the things that stood out the most viewing the eclipse was these large prominences coming off the side of the eclipse. And this one was the most obvious to me, but there are several others. And just to go to scale, these are probably several times the size of Earth. And I have a couple of figures here on the next slide giving more scale to that. These things are just huge, right? All of these little white things here are the corona, which is extensions of the sun's magnetic field. So at the very base level, the sun's a really big ball of hot ionized gas we call plasma. And it gets really dynamic at times because of its magnetic field. This is the source of everything space weather related, if you've ever heard the term. Also, source of the aurora is probably the most visible feature of that. So this is a sunspot. And I have the United States for scale and the Earth for scale. All of these little granular features here that you see along the outside, the same way that you have boiling water on the pot at home. Hot water boils up, cool water goes back down to get hot, and that cycles through. That is exactly what all of these little convection cells are at the top here. These are about 3 of them across the size of the United States. It breaks my mind a little, the scale of things. So a sunspot can be as large as Earth, sometimes several times larger. This is a video of observatory of a very particularly large one, and you can see it shift over the course of a solar rotation, which is about 2 weeks in this little video here. They are colder on average than the rest of the sun. Don't get me wrong, they're still very hot. The average sun surface is 5,000 Fahrenheit or so. This is slightly colder, 500, still very large. So these have very dense magnetic fields, which means that a lot of the major events coming from the sun are tied to the sunspots.
When you say magnetic, does that mean it has like a pole like we do?
So the sun has a magnetic pole, yeah.
Okay.
absolutely. And it gets really twisted. So I'll answer your question first. So just like Earth, the sun has a magnetic field. You know, it has a north side and a south side. During this cycle, we call it the solar cycle, that magnetic field gets twisted up. The sun rotates faster at the equator than it does at the top, and it drags the magnetic field with it. It kind of winds itself up. And eventually, it gets wound up so much, it gets tangled up and the magnetic field lines essentially snap like rubber bands and cause a lot of major activity. Right? As you can see here, this is kind of when everything's nice and back to normal, relaxed, solar minimum. This is solar maximum, everything's a lot brighter. This is a little animation of it. You can see a lot more activity going on during solar maximum. This is about an 11-year cycle, and we can track that cycle based on how many sunspots you can see at a given time. This is over the last, looks like about 50 years or so. Just go back so you can still see it, the picture. At the peaks of all of these things are where the sunspots are the highest. Right now we are at what's called solar maximum, or at least very close to it. So it should be no surprise that we see a lot more auroral activity, because when you have very strong solar activity, you'll see a higher chance of seeing strong aurora, making it down this far south. So solar minimum, low solar activity, solar max, high solar activity. From the people I talked to at the observatory about the aurora, last time we saw a good aurora in New Hampshire before 2024 was Halloween on 2003, which was approximately the peak of a previous solar cycle. So,
I saw that one.
yeah. Oh, good, oh, good. You're only 20 years late.
I know.
Oh, I was a little tyke and I saw it in Minnesota. So, yeah. So what all of this means, when I say solar activity in major solar events, I'm talking about solar eruptions. The most common terms for this that you probably have heard in some form is solar flare or coronal mass ejections. Right. Often these two accompany each other, but technically they're distinct events. They're not necessarily both. Solar flares are generally huge bursts of light, very high energy light, X-rays, gamma rays, and so on. And that's a result of this magnetic field snapping back together to reach a more stable state. I'll show you two videos here of coronal mass ejections. The one on the left is honestly fairly minor in the grand scheme of things, considering that most of it comes back to the solar surface. But keep in mind, this is still 2 billion tons of material, and they're very somewhat frequent, right? The one here on the right is from the May 10th event earlier this year, and all these little puffs of what appear like gas, these are again just huge things coming from the sun. This is a satellite observation of a coronal graph, and they have to put a little disk in front of the sun, just like an eclipse, so you don't blind your instrument. The little two bright dots here, that's Venus and Jupiter. And I just want to show you that video again. You'll see as the event goes on, you'll see more and more of these little white specks along the image. That's electrons interacting with the spacecraft electronics. It's just so strong. So that's what caused that aurora back in May. Okay.
And that was a solar flare.
That was a coronal mass ejection.
Oh, that was.
There was probably solar flares in there too.
Okay.
But-
Is that the one that gives us the light, the coral?
The ones that we really are interested in here are the mass ejections primarily. There's other things that do cause strong activity, but this is the big one, right? We all care about the plasma hitting Earth. So that's our first player. Number two, this one looks a little bit more familiar, I hope. So Earth has a magnetic field. If you have a big bar magnet at home, or maybe you had a science experiment in elementary school with a bar magnet and little iron filings, you can trace magnetic field lines from one side of a magnet to another, right? And you can pretend Earth is a big magnet. It goes from the south side up to the top. It's exactly what you think it is. It's not exactly at the North Pole. It's actually somewhat further south than that, it's offset. But that's not too important for what I'm talking about today. So when you have this big stream of plasma coming from the sun towards Earth, normally this is fairly minor. It's called the solar wind. It's just a breezy day, so to say, in space. That wind will hit Earth's magnetic field, and the magnetic field will act as kind of a shield of sorts and send that wind around the planet, up and around. Now, there's two sections of magnetic field that we have to care about today. There are what's called closed field lines, which means it comes out of one pole and goes back to the other. And this is on the front side as well as the back side. There's also what's called open field lines, which come out of the poles, which go from Earth out to meet wherever the sun's magnetic fields are. And what we care about for the aurora is this spot in between. It's kind of like this little gap in our shield. Plasma can travel down that and reach our atmosphere. It can also travel down here and kind of get stuck inside the middle. And I won't go over this one too much, but some of the material will get back even further, where our magnetic field will snap back and cause the night side aurora.
Cause the what?
Night side aurora. You can have day side aurora too. It's a lot harder to see during the day, obviously. But, so the way that you might want to think about this one is if you put a rock in a river, the water is going to move around the rock. That's exactly what Earth is doing with its magnetic field, with this plasma being sent out from the sun. But when you have a really strong event like a coronal mass ejection, some of that's going to make it through the shield and interact with our atmosphere. So the order of operations here, you have an eruption from the sun, hits Earth, it goes down the field lines just a little bit, and then it interacts with upper atmosphere air, nitrogen and oxygen primarily. One of the more interesting points to me when I was first learning about this, you don't actually get aurora at the North Pole. No matter how strong the storm is, you don't see aurora at the North Pole. You see it in what's called the aurora oval. This is where those field lines go from closed to open. It's where plasma can still make it out into Earth's atmosphere, but not get trapped, and it's not just escaping. Yes?
So does plasma carry magnetic energies? Do they set out this energy?
So I could answer it in a technical way, so I'm going to try to answer it not so. So when the solar wind comes out from the sun, it has kind of a baked in, frozen in, so to say, magnetic field with it. And there's not enough energy to change that magnetic field. My wife here, Nushin, probably can answer that better for you afterwards. She's the solar physicist in the family. But yeah, it's essentially a magnetic field that comes out with the sun that doesn't really change unless it interacts with other plasma. So, does that make sense? Okay. Okay. Good. Ask all the hard questions. So.
Thank God you're joking.
I know. Oh, I know. I'm the lucky one. So this is, the green here is where we normally see the aurora, right? This is northern Scandinavia, Alaska, Russia, Canada, and so on. When you have a moderate activity from the sun or geomagnetic activity on Earth, they come down a bit further south. Do note that even for moderate activity, it barely skirts the northern reaches of the US continental 48. This is what most of your headlines are from. It kind of reaches, it's a little bit there, but it's not really anything worth going out to look for. It's when you have a major storm that it's actually worth going to look for. That's the orange here. Okay. What is the aurora? At the end of the day, it's called the northern lights. The aurora is light emitted from molecules in Earth's atmosphere when they interact with this plasma, right? These little yellow things here are meant to be electrons coming down, interacting with nitrogen, oxygen, which then emit light. So I have to talk about chemistry a little bit here. So these electrons come down. First of all, do these diagrams look anywhere near familiar to people, or should I explain them a little bit? I'll explain them a little bit. So this is kind of the core. This is where protons and neutrons are, and all of these little kind of circles around them are called orbitals. These are different energy levels that an electron can occupy. Normally they want to be at the lowest one. They want to have the lowest energy they can. When this electron comes in though, it gives energy to the electrons inside of these atoms, and they get excited. They go to a higher energy. They don't like being here. So one way or another, they want to come back down. And when they lose this energy, they have to emit it as a photon. Photons are light. And based on what energy level you go from, you only can do it at very fixed wavelengths of light. So for example, the ones that we'll care about today, oxygen, atomic oxygen, will do that in red and green. Only two colors it'll do. This is also the basis of a whole other field of science called spectroscopy. It's how we discovered helium on the sun. It's actually the first time we found helium was doing this kind of science. The reason we call it helium is because Helios, the sun, is where we found it. So when this electron hits it, when it de-excites, it emits light. For oxygen, you can get green or red. So one of the key things about the aurora is its color, right? So there's two main constituencies about the aurora. There's atomic oxygen and molecular nitrogen. That's where two nitrogen are kind of paired together. And it depends on your altitude, depends on the density of the gas. As you get closer to Earth, you get denser gas. So the reason why oxygen here is emitting two different colors is because for red light, it's called a forbidden transition. It normally doesn't have time to just radiate away as a red photon. Normally just doesn't have time, but because it's not dense enough here, it can. This takes about 1 second, which is quite a long time on these atomic kind of scales. But once you get down further, you get denser gas, which means that you're going to get particles that hit each other. And once you start hitting each other, it doesn't have time to emit red light anymore. It has to go with the shorter option, which is green light. If this takes a second, this takes a couple milliseconds. Okay. Now for nitrogen, you got two different colors. You got red and you got blue. Difference here is yet one of these gases is ionized, which means it's missing one of its electrons. So it can go to a different energy than it normally would be able to. More of the nitrogen is going to be ionized the higher in altitude you get, whereas further down you're going to get more of this kind of neutral nitrogen, the stuff that will be in your lungs right now. Now, this kind of creates the very typical, I'll say, aurora structure where you have red on top, green in the middle. This is the most common color you'll see, and maybe a little bit of pink or purple down at the bottom. Now, depending on where you are relative to the aurora, if you're looking straight up, depending on general conditions, you'll get some combination of these. Sometimes you might see red or pink or violet. Maybe you won't see green at all, right? The one in October had a huge red patch, at least where I was. No green at all for that. There's green elsewhere in the sky, but not that one. So it does depend a little bit. The aurora can be very dynamic. Does anyone have any questions so far about the aurora? And we're going to get into a little bit more of how we study it here.
You have those massive ejections. Can it hurt any of our electronics?
Great question. I'll answer that later. But the short answer is yes. So these major storms can damage electronics on Earth. I have a slide later I'll show you, but the most clear example to me is there was a major storm in 1989 that caused rolling blackouts throughout northern Canada and the eastern US. I think some of the people here probably experienced that. I can't be sure. I wasn't in that area, nor was I born. But Dave liked my joke.
I did.
Yeah. So that storm induced a lot of current in the power grid, which ended up melting some of the transformers. And that's the reason for the blackout. So being able to predict when these storms occur not only will be nice for predicting the aurora to go and ooh and ah at, it'll also protect power grids.
Because what does it normally take when that projection happens? Is it like 1 to 3 days?
From the sun, it'll take about, 1 to 3 days. We have, so it's almost like you're a plant. So we have a number of satellite missions that can tell us when and where that ejection would happen, right? And we have them kind of spread throughout the solar system, that we have different viewpoints of the sun. So we can view the back, we can view the front, we can kind of pinpoint where it's coming from. We also have a lot of satellites at what's called the Lagrange point 1, which is kind of the gravitational balancing point between the Earth and the sun, that these satellites can orbit around for a couple decades. For example, ACE and WIND are in that position. We use these as a first good determination of what is the eruption made out of, how fast is it going, how dense is it, these kind of things. What's the orientation of the magnetic field? Some stuff that we can't otherwise see just from looking at it. And that would give us about 100-minute head warning. So we don't actually have a great system for this, and it's very difficult. It's why it's still an active area of research and why it's hard to get any kind of forecast beyond 3 days. So beyond those, we also have quite a lot of missions within kind of the Earth environment that can help us study what impact do these storms have, where are those effects most felt. And of course, there's also a couple in the outer planets, seeing how that affects. The other planets can help inform what happens on Earth. There's a lot of aurora on Jupiter, for example, and Saturn that Juno has seen. There's other ways that we can study aurora too. My favorite here is what's called the All Sky Camera Network. This is over the North American continent. These are cameras that just look up at the sky continuously, and you can piece them together to get the kind of global scale picture of the aurora. Now, the aurora does have local features, but it also has global structure to it. And by having all the cameras look up at the same time, you can piece that together. There's also magnetometers, which measure Earth's magnetic field. When there's a major storm, those will kind of like a seismograph on an earthquake, they'll bend out from the average. And you can gauge how strong this was or wasn't based on that deviation. And every little dot you see here is a different magnetometer around the world. It's a little bit hazy on this screen, but there's a lot of them. This here is an all-sky camera at the Poker Flat rocket range, which is where we launched the rocket. This is the night we launched. Just as an example. I'll show this picture again probably later. But there's other ways of doing it too. You can have a high altitude balloon, for example, that gets up to about 20 to 25 miles in altitude, and that can measure kind of a side profile a lot better than you can get down at Earth. Right? I'll talk about sounding rockets obviously in just a second. You can also have a lot of low Earth orbiting satellites. A lot of satellites on this previous page were quite a bit further out. By low Earth orbiting, I mean, within 500 miles in altitude. These can measure a lot more directly how much plasma is entering our atmosphere, for example, or is the atmosphere expanding. So this brings me to what I do. So we launch rockets. That's my day job. So dissipation here is the name of the rocket campaign. Sounding rocket, I'll get to that in a minute. Again, this is our mission logo. This is a kind of a big grouping of different universities that provide science instruments to measure stuff. We have NASA Goddard Space Flight Facility, University of New Hampshire, and this is the University of Maryland, and this is the University of Alaska Fairbanks. So first question, what's a sounding rocket? Right, these are not the big rockets that they launch astronauts in. A lot of the motors that we launch here, at least a couple decades ago, were mostly retired or outdated naval rockets. And we have repurposed them. NASA's bought them on the cheap from the Navy, and we're able to do a lot of good science with it still. Now, the good thing about sounding rockets is they're very low cost in comparison to a lot of other things to study. And they're very time effective, I would say. You can propose what you want to study, and you'll have it measured within 3 years, which is very fast turnaround time for some of these some of these science missions. The James Webb, for example, took 20 plus years to finish. So the sounding rocket program has been going on for well over 40 years at this point. I think they started in the late 60s. And we typically launch 20 plus rockets a year. I don't launch 20 rockets a year. This is the NASA folks. They're the rocket people. We are on 1 to 3 rockets a year at the University of New Hampshire. But
You do it right there in Durham? Do it right out of Durham?
we don't launch them out of Durham. I think you would hear about that a lot more. We build the stuff there, and then we bring it down to what's called NASA Wallops.
Where's that?
NASA Wallops. So Wallops flight facility is down in Virginia. It's on the East Coast, the little panhandle beneath Maryland. So
You get to go?
I do.
Nice.
We go for a lot of different things, and I'll show you that in just a second. But they have a lot of good people there. So why do we call it a sounding rocket? That might be interesting. So back in the day, 18th, 19th century, to sound something was on a ship. See how deep the water was. So to sound is to kind of like probe, and they kind of applied this to rockets later on to study the upper atmosphere. Now, one of the key things that sounding rockets have over other options is their altitude range. We can study things that balloons can't. Balloons can only go up to 20, 25 miles in altitude. Satellite missions, which are very effective in long term normally, if you bring them down below 200 miles, they burn up. They don't last very long. So rockets are kind of the only way to really study this very important transition region between space and our atmosphere. That's about 30 to 130 miles. You can change this altitude fairly easily though, depending on what rocket motor you pick. And there's a lot of different options here. If you want to go up high, you can pick a 4-stage rocket when you're proposing what you want to study. Or if you don't have to go up very high, you can pick one. I have a little cartoon version of me just for scale. So the one that we launched for dissipation is this one labeled 45 here. It's about 40 feet tall. It's about 7.5 of me. Some of these other rockets get up to 70 feet, and it's so tall I had to cut myself off. So, right, and you can do a lot of different things with sounding rockets. You can put a solar telescope on it, study the sun, proof of concept for a lot of different missions. I did that in my undergraduate days. You can also do what we're doing now, study the Aurora, different plasma physics in the ionosphere. You can also just do engineering tests, like what's the best way to fly a motor? What's the best way of measuring this or that? Right. These are all the locations that you can launch a rocket out of. All these green dots are places that we've launched a rocket from in the last 25 years or so. This one here is NASA Wallops. This is probably the main one. You aim off, shoot it in the ocean. This is White Sands Missile Range. It's in the desert. It's where a lot of solar physics happens. Solar telescopes. That one is New Mexico. So, the one that we're interested in here is Poker Flat, which is over near Fairbanks. I also had about a month over in this little island called Svalbard, but in Norway, but that's getting a bit off topic. So, the science goal for dissipation is studying how this aurora heats up our atmosphere. So, when these electrons come down the field line to cause the aurora, they're carrying an electric current with them. This current has to close. It'll go through our upper atmosphere across the pole and then exit out the atmosphere. Now, the same way that you have a toaster that gets hot, right? You apply an electric current through this, and the wire that is inside gets glowing red hot. It'll toast your toast. Right? This is going to have a resistance to it that's going to heat up the atmosphere. So the stronger your current is, the stronger your aurora is, the more heat you're going to generate. A really quick version of this is when you have a really strong aurora, you're going to have a lot of particles coming down your field line. The more electrons that come down, the stronger your current is going to be. We call this Joule heating. When you heat up a gas, it expands. So when you have a strong aurora, you're going to expand Earth's upper atmosphere. An obvious question is, why do we care? So it's a little bit hard to read, so I'll kind of go over this, but this is an article straight out of SpaceX's website. So this is with SpaceX's spin on it. So they have these big programs called Starlink. If you haven't heard of it, it's, for internet access around the world is the main goal. But they have a lot of satellites up and they launch a lot of them at once, right? So on this event in February of 2022, they launched 49 satellites into low Earth orbit at about 130 miles or so in altitude. Okay. But unfortunately for them, the day after they deployed them, a geomagnetic storm happened. This heated up the atmosphere, causing it to expand, which means where the satellites were, suddenly it's a lot denser, which means a lot more friction and atmospheric drag, 50% more. This resulted in 40 of the 49 satellites slowing down and burning up on re-entry. That's a pretty heavy loss. Of course, they launch these all the time, but still, you don't want this happening. It's a huge waste of effort. So if you can figure out how much impact you get to see out of a storm, you can predict, okay, maybe let's wait a day. Let's wait 2 days. Let's fly them an extra 10 miles higher. You can make corrections, but it's a difficult thing to study and it's not very studied well. This is part of what we're trying to help answer.
How long do they stay up there?
I'm not sure, to be honest. I think a couple of years is the goal. I would not be surprised if someone else here had a better idea of that, but a couple of years, I think, not too much longer than that.
So they need some sort of energy or power source to keep them maintained
Yep.
where they are.
A lot of satellites in these kind of orbits will have what's called an attitude control system, where they kind of have a tank of gas, of pressurized gas, where they can release that in a valve to push themselves back up. We have the same thing on the rockets to determine which way we're pointing. So, okay, so where is University of New Hampshire involved? The universities provide the science instrumentations as well as the science goals of these missions. So for this one, we have 2 instruments that we built. One of them is called an electrostatic analyzer. You can think about it as measuring these electrons that are coming down. How many and at what speed? This is the one that I was in charge of. We also provided what is called an ionization gauge, which measures how dense is the atmosphere, what temperature is the atmosphere at. So going back to WALLOPS now, we build these instruments at the university, we make sure they're working, we then bring them down to WALLOPS Space Flight Facility, and we meet up with all the other universities and their equipment, and we meet up with NASA and all of their stuff. And we have to make sure all of them talk well with each other. So we provide the science stuff, they provide the stuff like the radar communication system, the batteries, the hardware that actually launches the rockets, the motor, the facilities that they launch out of. So this is an example of a completed science payload. This is going on top of where those motors are. So if the motors are 40 feet tall, and this is another 10 feet tall, you add on another 10 feet to that. We do a lot of testing. We want to make sure that it's going to survive everything and not just explode. So, for example, we will build it up. We'll put what's called the rocket skin on it, this kind of outer shell, and we'll spin that. And we're going to aim to correct any balance issues. You want it to be as balanced as you can when you launch it. We also put it through a vibration test. This is a very, I'm not going to say violent, but it's very strong vibration that resembles the rocket actually launching. Sometimes, the story goes, totally never happened to me, the engineer will come back with a bucket of bolts that came loose. You really don't want that. If you have loose bolts, that probably means you didn't tighten them enough. So
No Loctite.
you really gotta tighten it. And sometimes you find issues. So this is Diana Swanson. She was in charge of the ionization gates for this mission. They had an issue opening one of the doors. So this is her plus the mechanical engineer from Wallops getting up on a forklift. This is, 20 feet off the ground, making sure what went wrong, what can we do better. We learn from this, we fix whatever the issue is, and then we test again. Right? Of course. It depends on the purpose of it. Primarily, it's mostly aluminum. Sometimes it's steel. Our main purpose is having something that's durable, but also lightweight. So, but sometimes it depends quite a bit. So, these little red caps at the top, for example, I think are covering up something that's made out of brass. So, yeah. This is the general size of the payload. This is, again, me for scale, this time not cartoon. So anyway, we do this test a lot. And my favorite test, or at least the one I like telling the most, is called the boom test. This one's not for the science instruments, but for the motors. They just put it on the launcher, and then they do the test, and the best result is nothing happening. Then you pass. If you fail, you know immediately, because it explodes.
Gives you that boom, right?
It gives you the boom. So, okay. So after integration, we bring our instruments back to our respective universities. We refurbish them, we recalibrate them, we make sure that any issues that came up are fixed. We then package them up. And this is 2 crates full of science instruments, or power supplies, or cables, or laptops, nicely snug together. And we go to Boston Logan, and this is 2 of those little trolleys. These things are a pain to move through airport security, I will tell you that. And this little white box here for this trip was 100 pounds. You can't fly anything above 100 pounds, so we had to reorganize it to be down to 70. So we had to take some cables into our carry-on. It wasn't anything important, but we needed to take it with just in case. So anyway, that was a little bit of a headache. So it was about a 13-hour flight from Boston over to Fairbanks, Alaska. Of course, the next question is why on earth did we go to Fairbanks? And hopefully you have a good idea of why. Right, Fairbanks is right here. And this green outline is the Aurora Oval. Fairbanks is pretty much right underneath it. So it's going to be very likely that we see strong aurora at this location. So when we actually want to launch, we don't have to wait 2 years. The other reason we come up here is the Poker Flat Research Range. This is a picture of the front entrance. This is where we launch our stuff out of. And over the last couple of decades, they built up quite a lot of infrastructure for it. Launchers, facilities to build stuff in, radar dishes, and a lot of ground observatories. Sometimes that means literal telescopes, like we're going to see later tonight. Sometimes that means magnetometers to measure magnetic field. Sometimes that means the all-sky cameras. That could also mean instruments that measure wind and density up to about 80 miles or so, just to provide a wider context to our measurements. Once we're at the range, we rebuild it. We do whatever testing we can. We're not going to shake it or do the boom test at this point. We still do the boom test, actually. But we put it together. This is the payload now fully assembled. This guy here is called the principal investigator. He's the guy that came up with the idea, sent in this proposal. He's the guy that gets to push the button that says go. So this is the team picture. This is me here. We have a number of NASA folks here, a number of scientists all working together. Now, when we actually put it on the rail to launch it, this is what it looks like. There's not really a visible rocket here, I will point out. You see, it's kind of like a styrofoam box. We put the rocket in a box for a couple of reasons. The main one is insulation, so it doesn't get frozen. You don't want any damage. But the other main one is we don't want anything inside getting wet. There's a couple of instrumentation things in here that when wet will no longer work well. So underneath here, you have this little tube that pumps in dry nitrogen to purge out any moisture. You want 0% humidity inside the thing.
And what happens once it gets out of the box? It doesn't have that chance of getting moisture?
Well, once it's out of the box, it's now in space.
Okay, that's where,
There's not enough time for it to get wet.
yeah.
So while we're up here, we're not only working, we're up there for 3-4 weeks at a time. So often we have little excursions, for example. We had someone's birthday while we were there. So we made rocket-themed and Aurora-themed pies, right? We went on a little hike and made a little snowman that we call Alfred, right? There is a lot of glaciers in Alaska, so you can go underneath some of these kind of ice caves. This is Nushin and I. We went cross-country skiing for the first time and kicked our butts. So we also
I was gonna ask you if you encountered any wildlife.
we had a lot of wildlife encounters. The story I'll tell here. So this is at our hotel. The background here is the gym. So Diana had her headphones in. She was just going on her morning routine. She's walking through the parking lot, checking something on her phone, and she ends up looking up and she's about 15 feet away from the moose. Now, I don't know if you've ever encountered a moose, but you gotta take them really seriously, because if they charge you, you're gonna be in a world of hurt.
They're very tall too, right?
They're like 6-7 feet tall.
Yeah.
If you have an adult one, they're bigger than you are for sure.
Yeah.
So she ended up having to just back away slowly, let it meander its way through to the woods, and then carry on every day. So these are some of the ones that we found out at the Missile Range. They're not, uncommon visitors, we'll say. And this is the road to the Missile Range from Fairbanks. So we got there in November, late October, early November. Still a lot of snow, but not yet totally frozen. So, how do we launch the rocket? There's a couple of things that we need to keep in mind in order to launch. First things, we need clear skies. Sometimes you don't need them, sometimes you do. For this one we did. We needed to make sure that there was strong aurora. And in order to do that, we needed to check the all-sky cameras at a couple of different locations around Alaska to make sure that the aurora is going on over where we'll be flying. The other thing that you have to consider for safety reasons is low surface winds. If you have a really strong wind gust, that's going to shift your rocket trajectory dramatically. And you really don't want to do that in case it lands somewhere that's not, that's populated. Yeah. So NASA's very careful about it. They have pretty strict rules about it, and it's a good thing they do. So this is the all-sky camera from when we launched. This is less than a year ago. Less than a year ago. 51 weeks, I guess. Okay. So the way that it normally looks is we're getting to the missile range in preparation for what's called the launch window. So at any given night, we have a 4-hour window where we can actually press the button to launch the rocket. And the reason why we don't stay there all night, other than people don't want to work 12-hour shifts, is because there's airspace and you can't occupy all the airspace for hours and hours at a time for weeks. It just doesn't work. So we're able to negotiate a 4-hour window over this portion of the sky. And we want to make sure we can maximize that. So we arrive early and we do what's called the count. So this is a very long, detailed spreadsheet of every task that needs to be done before we can actually launch it. Make sure the batteries are charged. Make sure the motors are armed. Make sure all the science instruments are working. What's the weather like? Do we see aurora or not? And we go through every single one, and there's someone on the radio that you'll hear going, yes, yes, go, go, go. I'm going to show a video, and you'll hear some of that chatter. This is the only thing that was live streamed, is this clock. This clock is in the Science Operations Center, and we stare at this all day, all night. When it gets to about T-minus 30, so 30 minutes before we could theoretically press the button and go, we hold it. We're waiting to see, is there going to be a strong aurora or not? If indications show, yes, there will be, we'll go down to T-15. And if it really looks like it, we'll go down to T-3. The reason we hold is here, we can have the rocket on external power. We don't have to use its battery. The battery itself lasts maybe an hour or so, but can't have it be on battery all night. Once you're holding it 3 minutes, you can't stay there for very long. You either go or you say, let's restart at 15. This is the night of the launch. This is out the window of the operations center. This is kind of us in the room. So I'm the guy in the blue shirt here, Diana's here. Boss guy here has his head looking at a computer screen. And we're looking at all kinds of things here. On the screen here, you can see the all-sky cameras in a couple different locations. You see a couple of graphs here. These are other science instruments to make sure that they're turning on and working. We're also checking the weather, the wind speeds. We're looking at our own set of instruments down here on our computers, making sure they're actually operating as we expect. If they're not, we say, don't do anything. So there's scientists in this room. There's a bunch of NASA people down by where the launcher is. They're in charge of the motors and actually turning on the power and so on. So when you watch the video here, just keep in mind, we're all going to run out. Okay? And I'm just going to sit back and maybe I'll narrate a little bit, but I think it's all pretty self-explanatory. Is there any questions before I do that? Okay, I'm just going to hit play.
EMA go. ETM. ETM go. EI. EI go. MM. MM go. TD. TD is go. Program, please take up the count at the top of the minute. 2 minutes, 1 minute, exactly.
We're all kind of rushing to actually watch it launch. We don't need to be at our station until 30 seconds after. Someone was watching the live stream from Fairbanks and had a camera on to watch it launch. This is the first stage motor. It's this two-stage rocket, so you'll see the second stage ignite here. And it's around this time where we all start running back into the room, making sure, is it working? We get really happy when things are working. We get the thumbs up from Boss Man. Good thing.
CM, we had a really great science run. Thanks to all for the great launch and performance.
So the entire launch was less than 10 minutes. Saudi rockets don't last very long. You know, they're kind of you gotta get the best data you can out of them. This one went up about 200 miles or so in altitude, which is above where the Aurora formed, so you can see it's coming down. And by all measures, we had a really nice launch. This is some pictures from it. So
How far away is that land? Like, do you get to retrieve anything off of it, or?
I have that on my next slide. As far as how far away it lands, it depends on what angle you launch at.
Okay.
This is in the middle of Alaska. You can have something that lands in the Arctic Ocean. This was about halfway to that.
Okay.
So it's not as far.
Yeah.
So It's a little bit hard to see, I'll admit, but there's a bunch of styrofoam down here that kind of explodes out
Yeah.
when you launch the rocket.
Now, what's going on in your stomach when all of this is happening?
Oh, you get really nervous. You get really nervous.
It's like, how many weeks or months of buildup for this one moment?
You generally more than a year, 2 years probably, depending. It depends on what point you as the scientist start entering the design and mechanical testing and so on. But,
But it's gonna be exciting and rewarding.
oh yeah, absolutely. I mean, yes. So when you launch one of the rockets out of this launch range, we're in the kind of a valley. This is what, we have a mountain in the background, the facility that we're at is on a mountain. And in the middle between those two is the launcher where you launch the rocket out of. It's pitch black. The only thing that you can see is the Aurora above you, but as soon as they ignite the motors, the entire valley lights up as if it's daylight.
Yeah.
And you can see a hint of that in the picture here. It's extremely bright for just that little moment.
Also, they go up in a giant arc and then they just come all the way back down and
Yes.
land wherever. So are they still, you said it got above the Aurora, so are they taking data on the way up, but all the way down as well?
Yes.
Okay.
So there's going to be a certain altitude at
Get
which,
your money's worth out of it.
yeah, we sure
Until
do.
they crash.
Yeah, absolutely, absolutely.
You're getting that information as it's going live. right?
Absolutely.
Yeah.
So on the rocket is something that we call the telemetry system. So this is going to be sending out our data in the form of like essentially a radio broadcast. And we have a couple of receivers around Alaska that will receive that data. Sometimes we might retrieve portions of the instrument and the data will be stored on board. For the instruments that we built, we got it from the NASA telemetry system. So as far as studying it, the entire arc, there's going to be certain altitudes at which our instruments would break if we opened them up. They're built for vacuum. So we start opening them up at, say, 50 miles altitude or something. Then we get all the way up, and then we don't bother shutting them down. We milk them for the best we can.
Yeah.
So another little thing I'll point out, you have a little green laser here. Dave, do you have a laser pointer you use for your shows?
Red.
Red? Okay. Same thing. If you ever seen one of the laser pointer shows at a Astronomical Society event, we have a really big laser hooked up to a telescope here. This is one of those ground support observatories. This one here is measuring wind and temperature. So,
Isn't it that the green are stronger, they go further?
I'm not sure, frankly.
Yeah, because I know when we have for work, we had the red, and then we went to a green, and said, get a better distance.
I'm not sure.
measurement.
Yeah, maybe. I think the reason we use green here is because it's more visible to some instruments. So once we have it launched, we saw a couple of posters that I thought were really fun. It's bounty hunting, essentially. If you're a pilot or a hiker or a hunter that's going out to the wilderness in Alaska, if you find where these rockets landed and report them back to the launch range, you can get paid money. It's a nice little bonus.
Do you have a little black box on them?
I think that's what they're moving towards, but there's going to be debris that just breaks off from the rocket.
Sure.
For example, this is a recovery effort that they did, not for our rocket specifically, but for a different one. They had 2 helicopters that flew out. They were told where the thing was. They landed nearby, they had a bunch of straps. They had to dig it out of the snow. And of course, this is the rocket getting dragged by the helicopter all the way back to somewhere to recycle it.
Are they pretty hot still when they hit the ground, so they melt into the snow, or?
I don't think they're hot, but maybe. They're fairly sturdy, but sometimes, depending on what angle you hit the ground at, they can really kind of fracture off.
Yeah.
So some of these rockets have fins to help aerodynamics.
Do they have a parachute?
Some of them do. Most of them don't. Parachutes are a complicated system to make work. They do it if the equipment's expensive. So we had a parachute on the one we had for half of the payload. And I got the lucky side. I got the one with the parachute. So I promised at the beginning I would go over how to look at the Aurora at home. So here's how I would recommend doing it. you gotta look up a forecast for the geomagnetic activity for the night. And the specific thing that you're looking for is called the KP index. This is an index of geomagnetic activity that goes from 0 to 9. A 9 is really high activity. To see the aurora down in southern New Hampshire, you're looking for a KP number of 7.5 or more. For the aurora display that we saw in May, it was a 9. For the one in early October, I think it was an 8. So if you see anything below a 7, again, there's a chance, I won't rule it out.
Your camera might pick it up, right? But
Your camera might, but it's going to be very dim.
Yeah.
So there's this chance, but it's not necessarily a go for it, spend an extra hour outside. So the specific thing I'd recommend is looking up stuff like KP index forecast or aurora forecast or geomagnetic activity, geomagnetic storm tonight. And one of the first couple of results that you'll see is the NOAA Space Weather Prediction Center, the dashboard on it. Yeah.
So what's the other rating they have? Is it like 4G? There was something they said it was gonna be a 4G, but is there a conversion to go to the KP?
There's a couple different indexes to use. The one that I'm going to recommend here is KP. Yeah. There's also solar flare classifications, like if you have an X-class flare, that's a lot of activity,
Okay.
for example. But I think this is the easiest one.
Said something like a 4G or something, or a G4.
I'm not sure which one that is.
Yeah, I didn't know. So that's like, that's not helpful me because I'm looking at, like you said, the
Yeah.
KP.
Yeah.
So,
Yeah, there's different things, but
yeah.
okay, anyway. When you go to this website here, these are kind of the plots that you'll see. So this is the kind of time history of the last 2 days for KP index. I picked up this one yesterday, so this is over the last couple of days anyway. It's been fairly low. There's been nothing noteworthy. They also give you a 3-day forecast. You can't really go anything past 3 days because the uncertainties become very large. But it will give you a rough estimate of, oh, there's going to be a big number coming up in 2 days.
Yeah.
You really want to check it probably a couple hours beforehand too to see, did that number get updated?
Right.
So
So they give you a KP number. They don't do it hourly, right? Or do they?
they do it every 4 hours.
Every 4 hours.
Every 4 hours. They break into 4-hour chunks. When you use at least this website specifically, the times they have listed here, I will note, are in British time. So you have to move 4 hours or 5, depending on daylight savings, to get it over here. So, for example, the top line here is 0 to 3, which is midnight to 3 a.m. That would be 8 p.m. to midnight here. So this down here gives you examples of what the aurora could look like for different KP indexes. So this is 3. This is a very mild aurora. The color here is the likelihood. Red is very likely. Green is like, maybe. For a KP index of 5, yeah, you'll see it in Canada probably, Alaska. But continental US, maybe. Probably not.
Way up high, right?
It's only when you get to 7 and 9 where you actually get down to New Hampshire, where we are living right now.
So why is it dipped down like,
Like this.
yeah, down there, like,
I think the main reason for that is it's midnight. So the way that this plot here is, the sun is right here. So this is local midnight. So this is local noon. And I think the strongest aurora comes around midnight to 2 a.m. generally. So, and that has to do with, the orientation of magnetic field and how the solar wind interacts with our magnetic field.
So when we get in the north, do the south get them also?
When we get the southern hemisphere, yes, yes.
So,
I know a little bit less about that specifically, but yes, the northern lights have a southern light counterpart.
yeah,
I think it's the Australis borealis, I think.
okay.
I might be pronouncing it wrong, but yeah.
What chance does the Mount Washington Observatory have to see this more often than we would see it because of what they have to hide and?
I think the primary thing has to do with latitude. So they are further north by about 2 hours, so they will see it more often than not, compared to us. But it's
The other
still,
good thing is they're a lot darker too.
yes, that's also a very excellent point. They're in a very unlight polluted area. That also helps quite a lot. So especially if you have a fairly dim aurora, you don't want to be in the middle of a city. So, and this is that picture again. Are there any questions about anything else? Feel free to.
You did a very good job.
Thank you. Yeah.
I've always wondered why you have the magnetic lines coming in like that.
Yep.
And so some of the irradiated particles coming to the atmosphere through that. What gives them that like curtain look? And is it moving or is it just static for 10, 15, 20 minutes at a time? And it doesn't come down all the way, so does it get kind of burned up in the atmosphere before it hits the...
There's a couple of pieces in there that I can answer. First one, the last thing you just mentioned, the reason the aurora doesn't come down further in altitude, the more dense the atmosphere is, the harder it is for these charged particles to actually get down. And around 50 miles or so, it's so dense you no longer get any charged particles, you don't get any light. That answers that question. These things are rarely static. Sometimes they last for a minute, sometimes they last 30 minutes, and sometimes they are mostly in the same place, sometimes they dance around. Sometimes they have very beautiful arcs to them, sometimes they're very diffuse. Sometimes they look like what's called a picket fence, where they have juts up here and here and here, but otherwise they're kind of sparse in between. There's a lot of different categories of aurora that I'm not an expert in, quite frankly, but it does vary quite a lot. As far as why they come down further south and so on, that's a little bit harder to answer, to be fair. The more plasma that comes down, you need a larger area to kind of get rid of that. The other thing to keep in mind is the Earth's magnetic field isn't static either. It has an interaction with the incoming plasma. So when you have a big burst of plasma, some of these onion layers are going to get peeled back, so to say. I'm going to just jump back quite a bit here, just to answer that question. So for example, when the solar wind hits this front one here, it'll kind of peel back, and some of that will actually fold back. So then it can come down lower. That's why I think it probably goes down into lower latitudes. But as far as why they are shaped like this, I'm a little bit less sure. It has a lot to do with small differences in magnetic field and the upper atmosphere.
And nothing to do with the US government, right?
The US government controls the aurora.
Well, then you better tell them to step it up.
Yeah. So we have to, we study part of it for national security reasons, but we don't control it, unfortunately. I think it'd be fun if we could.
So the other question they said you'd get back to was about what damage it could cause.
Oh, yeah. Let me go to my backup slide. So here we go. So this was a result of that 1989 storm that caused blackouts in Quebec and the East Coast. This is a transformer that had so much current running through it, it melted. So one thing that we want to be able to do is disconnect these from the grid when we need to, or improve the design of this so it can handle higher currents than we're expecting.
So it's true that if they're disconnected, you could be safe with your electronics?
To some extent, yes. But that's only true to some extent.
Yeah.
You can have what's called a ground-induced current, where the actual ground itself will induce a current, which could presumably also damage things.
Okay. And a Faraday cage would protect those?
I'm a little unsure. That's kind of an active area of improvement. Other things to watch out for: if you have a really strong storm, your GPS signal is going to be a little bit funnier. For most people, I don't think it's going to matter, but if you have a very technical thing that you need to be precise with, being off by a couple meters might be a huge difference.
So does that also go by the KP index?
Yeah.
So
There's different types of indexes.
what would be a threatening index?
It depends on where you're living. For this kind of damage here, probably a 9.
So a 9 could be.
Probably.
something that's a-
You'd want something very strong.
Can it cause your lights to dim at all?
That would probably be more like your power company. But
Does it have any effect on, like, it's like, can it cause like headaches for residents?
not that I'm aware of. That could be a very interesting question, quite frankly, but I just don't have background on that. So, yeah.
How much does it affect for our weathermen to be forecasting our weather? How much impact does it have on our weather and how they forecast it?
Mhm. For traditional weather like rain and wind, I don't think it's a significant difference. There's going to be some because you might have satellites that are being used to model and take measurements of the regular weather, and those might be shifted around a little bit based on the storm, but I think mostly it's unaffected, maybe mildly. So, the other thing I'll point out is especially over the polar regions, if you have a really strong storm, you no longer are able to send radio signals off the top of the atmosphere. Normally you can have like a ham radio, send out a radio pulse, it'll bounce off the top of the atmosphere and come back down. You can get signals very far away with that. That's kind of how you might communicate with a plane, for example, or a ship in the middle of the ocean. If you have a really strong storm, you can lose communication pretty easily. Because the atmosphere up here gets really dense and it comes way lower, if that helps. Of course, when you have a strong storm, you might also damage satellites or astronauts that might be orbiting. That's kind of the main points of damage to worry about. Anything that has a lot of tech in it can get really affected by this stuff. So, yeah.
Are you familiar with the SAR arc and if there's any relation to Aurora? I was able to capture a photo on October 7th that had Aurora and SAR arc in it.
It sounds familiar. Can you explain what SAR is?
So I just did some research on it.
Sure.
I'm not sure exactly what it is. Like, I just know that the arc that was going over the sky at the same time as the Aurora was not, at first I thought it was a part of the Aurora, and then I learned that it wasn't.
Is
can show
it
you.
lightning related? Yeah, if you could show me afterwards, I think that'd be very interesting. Because there's some very strange aurora. There's some stuff that's called black aurora. I don't know anything about that, but I definitely saw it on the Wikipedia page. There's also a lot of interesting lightning things that happen that are somewhat related, but or not dependent necessarily on the sun or anything like that. So, same type of physics though. Yes?
You wanted to travel up north and hedge your bet on being able to see the aurora. Is there a better time of year to do that?
Definitely not the summer, because then it's going to be daylight very frequently. So you want to go probably, when it's darker. I wouldn't say the winter, because winter in Alaska kind of isn't pleasant. So I would recommend probably either kind of late fall, like October, November, or kind of early spring, March, April.
Is Iceland a good place to?
I think so. Where is Iceland on these maps? I know Iceland is very famous for its aurora. I've had people that go there and spent 2 weeks there, and it's either cloudy all the time or they just didn't get very lucky. So, but I think the answer is probably yes. Oh yeah,
You also,
Tromso's great.
that Aurora app also will give you all the locations
Yeah.
where it's active.
Yeah.
And you'll get to see many of the common places.
Yeah. So, I think on this map, Iceland is underneath that wall. It's probably around here. It's very hard for me to see. I'll point to it on, it's right there where my mouse is.
Yeah.
So, You can definitely see, you just need something slightly stronger than average. Yeah. Yeah.
For your concept, this will be where you are now, we studying undergrad and so on, and you'll be able to go next after.
Sure. So for my undergrad, I just kind of went in as a physics major. I didn't really know what I wanted to study other than science was cool. The first research position that I got was in a field called space physics. It's a little bit misleading at times, called space physics. It's only within the solar system generally. It's anything from Earth's upper atmosphere, which is kind of what I'm doing right now, through the magnetic field to the sun. Solar physicists, despite not really like being associated with us, are still under space physics. I love you, honey, don't worry. It also includes stuff like the outer planets and stuff. So the project I was working on there was studying the solar wind. And a lot of stuff that I was interested in at the time was kind of like coronal mass ejection type things, but nothing super specific. It was kind of whatever project my advisor thought was useful to look into. So when I was applying for grad school, I was like, okay, I like this field, it's really interesting. I want to get a little bit more hands-on with stuff. So I came to UNH, which has kind of this space science center. There's a lot of engineering that goes on as well. And the rocket program seemed like a perfect fit.
And where did you come from?
I came from Minnesota.
Minnesota.
So, yeah. You know, well, it's,
It's chilly up there too.
it gets quite a bit colder in Minnesota, I will say. It's a lot hotter too. So, I think all around I prefer here.
How long have you been here?
2019.
Okay.
So, but in terms of after graduating, probably will graduate next year. So if anyone has a job, well, we'll see. There's some options that I think will be very nice. I could presumably stay around. I have a couple of contacts from doing all the rocket stuff down at, for example, Goddard, or wherever they take me. You know, I'll be happy to go wherever, frankly. It's just an interesting thing to do. Yeah.
Would NASA be an option for you to?
Oh yeah, absolutely, absolutely. They were part of the team that did the sounding rocket, so you know, I could even join the NASA side that does the rockets. I'll be an actual rocket scientist instead of just using the other. Yeah. So. Yeah.
Do you both get to go together?
Oh, wherever we're going to go. Yeah, she came up with this one.
No.
So.